Hi, I'm Jeff Mucklin. I'm with the Nurture Nature Center, and this is Science at Home. And you might be able to tell that I'm pretty cold right now. I'm wearing relatively warm clothing, but it's about 32 degrees out here, and the wind is blowing, so I'm a little chilly. But cold can be very dangerous, and extreme cold is even more dangerous. The coldest temperature ever recorded in the Lehigh Valley was minus 15 degrees Fahrenheit, and that record was set on January 21st, 1994. But it's far from the coldest temperatures that we see on the Earth. To see those kinds of temperatures, you have to go to the North or South Pole. I'm back at the Nurture Nature Center, where it's certainly much warmer, and I can use the science on a sphere here to show you these warm and cold places. So if I just tilt the sphere towards the North Pole, you can see that it is much colder there. We're using color to represent temperature, and you can see the North Pole is a very cold place. You can also see that high mountain ranges are very cold. The Rockies are cooler than the landscapes around them. Towards the South Pole, you can see that it is also a very cool region, a very cold place. All objects emit infrared radiation, and we can use that to tell how warm they are. We're familiar with the fact that really hot objects will actually glow red hot. You can tell that a piece of metal is hot if it's glowing red. But even I am emitting some infrared radiation that I can't see. You can't see it either, but this can detect it. And by pointing it at, say, this jar here, I can see that this jar is 149 degrees Fahrenheit. And if I point it at this jar, I can see that this one is 33 degrees Fahrenheit. I was able to measure their temperature without touching them. There are other ways that we can measure temperature. One of the cheapest tools for measuring temperature is a bimetallic strip, which is just two different pieces of metal that are stuck together, and different types of metal expand and contract at different rates depending on what temperature they are. So with this bimetallic strip, when it's cold, it bends in this direction. It's bending over this way. But if I heat it up, it will bend in the opposite direction. So I'm going to put it in the hot water, and now it's bending this way. Another thermometer that you've probably seen in some of my other videos is a Galileo thermometer. This uses changes in the density of a liquid to tell us how warm the environment is. The clear liquid becomes less dense the warmer it gets, and the globes floating within it can't float. They're not buoyant enough if the alcohol becomes less dense, and they start to sink down, and you can tell what temperature it is by simply reading whatever the bottom globe still floating indicates the temperature is. But by far one of the most reliable ways to measure temperature is just with a simple thermometer. A thermometer like this one has a liquid. It has alcohol inside of it, and I'm going to take it out so we can see it more clearly. There's a blue well of alcohol here, and that alcohol expands and contracts with the temperature. So what is temperature? What exactly is it that thermometers are measuring? Well, simply put, temperature is just the average kinetic energy in the atoms and molecules that make up all the material that around us. It's the average kinetic energy in gases and liquids and solids. If something has more kinetic energy, if its atoms and molecules are moving more, it's a material that's hotter. And if they're moving less, if they have less kinetic energy, it's something that is colder. Can the kinetic energy actually drop to zero? It can. We call that absolute zero. This is the coldest possible temperature, where the atoms and molecules are not moving at all anymore. It's actually not possible to reach absolute zero, though. For reasons I can't get into here, having to do with quantum mechanics, you can't quite suck out all of the energy, all of the kinetic energy out of a material. There's always at least a little bit left. Well, heat always moves from areas of high heat to areas of lower heat. It never moves the other way around. And there are really just three ways that heat energy can move from one object to another. That's through convection, conduction, and radiation. Convection occurs when an object is warmer than its surroundings and becomes less dense and actually moves. This is a very efficient way to transport heat. Warm air masses can rise up into the upper atmosphere and bring a lot of heat and moisture up with them, and they can power thunderstorms. Another way that heat can move is through conduction. This occurs when the material that's hot can't physically move to the material that's cold, but the heat still moves through these objects. A good example of this would be right here on the table in front of me. I have two plates of copper. One copper plate is hot and one is cold. I'm going to put the cold one on the hot one. Now the heat will begin to flow from the warm copper sheet into the colder copper sheet. Okay, so it's been about actually 30 seconds. Hot plate is now 104 degrees and dropping, and the cold plate is now 70 degrees and it's rising. And if I was to wait a little bit longer, eventually these would reach the same temperature. So there's one other way that heat can move, and that's through radiation. Thermometer at it, and I can see that the bulb is 120 degrees. So that heat energy can move through space. It can move from its source to this black tile. And it's heating up the tile. The tile is currently 72 degrees. And if I check back here in a short while, I'm sure it will be warmer. The sun is able to radiate heat through the vacuum of space. The sun is 93 million miles away, but the energy from the sun is able to reach the Earth through radiation. And if we check back at our tile, it is now heated up to 77 degrees. So we have convection, conduction, and radiation. Knowing how thermal energy moves allows us to better protect ourselves from the cold. And the human body does need protection. We are not well adapted to surviving in cold environments. If you add to a cold day, even a mild breeze, we can feel even colder. This extra cold feeling that we get from the wind is called wind chill. That's what meteorologists refer to it as. And it's just caused by the fact that our bodies create a thin layer of warm air around us. But if the wind blows, it disturbs that layer of warm air, and it removes that insulation, and now we feel much colder. But just adding a little bit of insulation protects us. So I have a beanie that I was wearing. This is an emergency blanket. It's very shiny and reflective. And if you wrap your body in this, it allows you to retain your body heat by preventing you from radiating it away into your environment. One more way that we can stay warm is to generate more heat. And there's a few ways we can do that. One way is to use electricity. If we pass electricity through a material with a high resistance to the flow of electricity, that thing will heat up. That's how the filament in a light bulb works, like this one. This is a heat light. You can also produce heat through friction. Just by rubbing your hands together very quickly, you can feel heat building up on your hands through friction. We can also generate heat through chemical reactions. Chemical reactions that produce heat are exothermic. These hand warmers perform an exothermic reaction, and they generate heat. They can actually produce heat for up to 10 hours, it says on the package. And the powdered iron is oxidizing. It's reacting with the air, and as it does so, it slowly begins to heat up. For this at-home activity, you're going to need some fine steel wool. You're going to need a styrofoam container with a lid, and you're going to need a thermometer, which you're going to have to put through that lid somehow, and you're going to need some vinegar. And what we're going to do is we're going to pour this vinegar over the steel wool, let it soak into the steel wool, and then we'll dump out the excess vinegar, and we'll put our thermometer and our lid back on top. And what's going to happen is the vinegar is going to remove a thin layer of rust that's protecting the iron from oxidizing, and it will then begin to rapidly oxidize, just like our chemical hand warmers. And that should cause the temperature to rise inside of our cup, which we should see with this thermometer. We should see that blue line begin to move. It's been about 5 minutes, and I've actually been really impressed with this because the inside of our container is now 41 degrees Celsius. That's about 105 degrees Fahrenheit. So it's actually doing better than the chemical heat packs that you purchase. I imagine this is going to continue producing heat for a long time because the reaction is still occurring. And if you go outside this winter and it's cold outside, just make sure that you bundle up, wear protective clothing, keep yourself insulated and protected from the cold, and enjoy the rest of this winter. See you next time.